Chapter 10 in the abstract algebra series is divisibility properties of the integers. Problem number 1 says, what are the quotient and remainder when 32 is divided by 5? Okay. According to the division algorithm, any integer n can be expressed as the product of a quotient times a divisor plus some remainder. So in problem number 1, our number n is 32. And since we're dividing by 5, 5 would be the divisor. And 5 goes into 32 6 times. And 5 times 6 is 30, which means that the remainder is 2. So the quotient would be 6 with a remainder of 2. And again, that's the division algorithm. Number 2, what are the quotient and remainder when negative 32 is divided by 5? If you go back and look at the division algorithm, there are some restrictions on D and R. It says that D has to be greater than 0. And we know that the remainder has to be at least 0, but less than the divisor. Because the remainder is how much is left over after you divide by D. So if we stick to the division algorithm outright, here n is going to be negative 32. And if we're dividing by 5, again, 5 is the divisor. So I'll have negative 32 in place of n. 5 is the divisor. But if you look at the restrictions in the division algorithm, R has to be greater than or equal to 0 and less than D. So for that to happen, what we have to do is we have to take multiples of 5 that go beyond negative 32. So if you start at 0 and you go back multiples of 5, we're going to the left. If we take multiples of 5 and we stop on the other side of negative 32, we will end up at negative 35, which means we went back 7 chunks of 5. So negative 7 is going to be our quotient. And since the remainder has to be positive, in order to get to negative 32, we would have to add 3. So negative 32 is going to take us back 7 units of length 5. That puts us at negative 35. And then we will simply add the remainder 3 to get back to negative 32. So the quotient would be negative 7, and the remainder is positive 3. Problem number 3 says to restate the division algorithm so that it applies to both positive and negative divisors. In order to do that, we just make a slight modification. We're going to say that for any D that's not equal to 0, because division by 0 is undefined, so D cannot be 0. So for any D that's not 0 and A, there exists a Q and R, Q being the quotient and R the remainder, such that A is equal to QD plus R. If we want to rewrite the division algorithm so that it applies to both positive and negative divisors, we will simply encase the D in the absolute value bars. So if D happens to be negative 3, then the absolute value would be positive 3. And we could use the positive 3 in the equation. So let's look at number 4. Number 4 says, what are the quotient and remainder when negative 32 is divided by negative 5? Okay, so this time our divisor is negative 5, which we are going to allow because of the modification that we made to the division algorithm in problem number 3. So negative 32 is going to be 7 units of -5. That's like going back 7 times, and each chunk is -5. So if you go back 5 chunks of 7 on the number line, that is going to put you at -35, and then you would add 3. And as you know, 5 times -7 is the same as 7 times -5. So this problem is essentially the same as number 2, since we made the modification allowing d to be any integer other than 0. Number 5, using Euclid's algorithm, determine the GCD of 184 and 80, and then compute x and y such that 184x plus 80y is the GCD of 184 and 80. Euclid's algorithm asks us to rewrite 184 using the division algorithm. So 184 is going to be 2 units of 80. Now, why did I choose 80? Because we're looking for the GCD of 184 and 80. So that's where the 80 comes from. So 184 is equal to 2 units of 80 plus 24. And then we simply shift the divisor and the remainder over to the left, and we continue the process. In other words, on the second line, my divisor, 80, is going to go to the far left, and I'm going to move the remainder 24 up. And that means that 80 is going to be 3 chunks of 24 plus 8. And we just continue the process. On the next line, the 24 goes to the far left, the remainder of 8 moves up, and then I express 24 as 8 sets of 3 plus 0. Once we get to a remainder of 0, then the last divisor would be 8. Since the last divisor is 8, 8 is the GCD of 184 and 80. Why would it be the case? Because if we go back to the very beginning of the problem, we know that we have to express 184 in terms of 80. Well, if the last divisor is 8, we know that 8 goes into this entire right side because 8 goes into 8 times 3 and 8 goes into 0. And since we would not have a remainder on the right side, that means that 8 goes into 24. So if 8 goes into 8 and 24, then that means if I go to the line above it, 8 would go into this 8, 8 would go into the 24, leaving no remainder on the right side. Therefore, 8 must go into 80. Since I've already shown that 8 will go into 24 and 8 will go into 80 without leaving a remainder on the right side, then 8 must divide 184. So the GCD is 8. And then if we use repeated substitution, we can show that 8, the GCD, is a linear combination of 184 and 80. And we just do that by back substitution. If we go back to the last line in the problem, we know that if we go to the second to the last line in the problem, we know that 8 is equal to 80 minus 24 times 3. I just subtracted 24 times 3 from both sides. So 8 is equal to 80 minus 24 times 3. And if I go to the top line, I know that 24 is 184 minus 2 times 80. So I'm going to substitute in for this 24, 184 minus 2 times 80, still multiplying by 3. And that's going to give me the GCD expressed in terms of only 184, or expressed in terms of 184 and 80. Using algebra, this is going to give me 80 minus a negative 6 times 80. I will add that. That would give me 7 80s. And then I have minus 3 times 184. So 8 can be written as 7 times 80 minus 3 times 184. Therefore, our value for x would be -3, and our value for y would be 7. So I can express the GCD as a linear combination of 184 and 80. Problem number 6. Problem number 6 says, that should say list the elements in U12, where UN is defined as the set of positive integers less than n that have no prime factors in common with n. So the positive integers less than 12 that are not relatively prime to 12 would be 2, 3, 4, 6, 8, 9, and 10. Therefore, all of the composite factors that divide into 12 would leave me 1, 5, 7, and 11. Number 7, show that the square of any integer is equal to 3k or 3k plus 1, where k is an integer. Well, by the division algorithm, we can express any number or any integer n as 3 times q, or 3 times q plus 1, or 3 times q plus 2. If I can express any integer n in either one of these 3 ways, then I need to show that if I square any of these 3 ways, I'm going to get 3 times k, or 3 times k plus 1. Well, let's square n in the first case. Well, n squared would be 9q squared, and I can write that as 3 times 3q squared, which would be 3k, where the 3q squared is k. If I square the second way of writing n, if I square 3q plus 1, that's going to give me 9q squared plus 6q plus 1. And notice I can factor a 3 out of the first 2 terms. That leaves me 3 times this k plus 1. And the reason I know that is an integer, because if you multiply an integer times an integer squared plus twice an integer, you're going to get yet another integer. So this is going to be the 3k plus 1. And then finally, if I square the 3q plus 2, that is going to give me ultimately 3 times this k plus 1. So any integer n, if you square it, would be equal to either 3k or 3k plus 1. Number 8. The smallest positive multiplier theorem says that in general, if k and n are positive integers, then n divided by the GCD of k and n is the smallest multiplier of k that yields a multiple of n. What would be the smallest positive multiplier of 12 that is a multiple of 42? Well, if we just employ the formula outright, in this case, n is equal to 42, because we're looking for something that would yield a multiple of n, in this case, a multiple of 42. And it has to be a positive multiplier of 12. So 12 is going to be our k, because in the definition, we're looking for the smallest multiplier of k, so multiplier of 12. And if we use Euclid's algorithm, we would find that 6 is the GCD of 12 and 42. We're going back to the formula and plugging in 42 for n, and then 6 for the GCD of k and n. 42 over 6 would be 7. So 7 would be the smallest positive multiplier of 12 that is a multiple of 42. Notice that 12 times 7 is 84, and 42 times 2 would be 84. Number 9. Give an informal argument that x divides z if x divides y plus z and x divides y. Well, both y plus z and y must be multiples of x if x divides those. We cannot have a non-zero remainder when either value is divided by x. Well, that means that y plus z divided by x, if we separate that fraction into two fractions, then y plus z divided by x would equal y divided by x plus z divided by x. Well, the first factor is an integer since x divides y. And the second factor would also have a remainder of 0, and that would occur only if x divides z. Problem number 10. If you were to express 50 factorial as a decimal number, it would end in how many zeros? Well, the trick to this is we begin by finding the number of 5 factors in 50. So if we list those values that are divisible by 5, then we would have 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. All of these will have 5 factors. Well, how many factors of 5 does each number have? Well, 5 would have one factor of 5, 5 times 1. 10 would have one factor of 5, 5 times 2. 15 would be 5 times 3, so it only has one factor. 20 would be 5 times 4. 25 is going to be 5 times 5, so it would have 2 factors. And we basically just continue this, counting the number of 5 factors. If we add up the number of 5 factors that appear in 50 factorial, we would have a total of 12. Well, if you have any experience with working with factorial, you know that factorial is notorious for spitting out a lot of numbers that are divisible by 2. So if there are 12 factors, 5 factors, if there are 12 5 factors, I know that there are at least 12 2 factors, and 5 times 2 is 10, which means I have 12 factors that are 10 factors in 50 factorial. Therefore, the number 50 factorial would end in 12 zeros.